But now that Mitch has shown you the care project from somewhat of a user's perspective, we thought it'd be interesting to give you a peek into the automated testing that we've been using to try to make sure it's doing what we intended it to do. So to speak about a little bit about why we set up the automated testing, the overall care project actually includes both Python-based package code and, of course, XML-based templates. And I think there's currently over like a couple of thousand lines of Python code, and the templates at this point, they're over 70,000 lines. And they, of course, the templates have their own logic with blocks of processing instructions handled by the template, NSO's template engine. And as you can imagine, all this would be really difficult to test manually whenever a change is made to any part of that. The changes, you can imagine they can include changes to the Yang model, which we just introduced a major change, was Mitch mentioned for the 2.0 part. So that was a kind of a big change to the model. Could be changes to the Python code, could be changes to the template code, and it could be we want to switch over to a new NSO version, or or more likely it could be that one or more new NED versions have come out, and we need to validate all the templates against those. And of course, new NED versions come out every week or so, so that's a pretty common event. And our goal was try to make the testing for this as robust as possible. So we have hundreds of both passing, currently have hundreds of both passing and failing tests in our test scripts to try to ferret out any issues that might be lurking in the various pieces of the project. And in the backs of our minds, we'd like to reach the point, not there yet, but we'd like to reach the point where the tests would be created first, basically kind of akin to a test-driven development from a more pure software approach. And obviously, of course, one of the major goals is to catch as many issues as we can before the project ends up in a user's hands. So when you're working to add new features and support additional STIGs, like in this case, revalidating the stuff you've already done sometimes takes a back seat to new work, people asking for new features. So case in point, when we introduced this automated testing back in the spring, we immediately found a handful of issues in some of the templates that were coded early on in the project that just hadn't been exercised recently. And it could have been a net issue or something, but anyway, so we found some issues pretty quickly and fixed those. So to give you an idea of some of the pieces involved with the current testing setup, of course, the project's hosted in an internal repo. It's actually split across two repos, but we make standard use of webhook notifications from the Git server for that when a change is pushed up to the repo, and it could be pushed by any one of us. And Jenkins is currently our primary continuous integration tool of choice for handling this test pipeline. And it's the Jenkins instance we have is not only hosted in a Docker environment on an internal server, but it also runs our various test stages using Docker containers. And we'll see a little bit more detail about that later. And one of the, of course, basic steps we do is just to check the code hygiene / quality, which is, really looking for syntax errors and formatting, issues in both the package code and the template code. And for Python, we check adherence to best practices, of course, for style using PEP8 rules, which are pretty common. And we also do a bit of static analysis through the Pylint tool because it's capable of it. And if you haven't heard of static analysis before, it's the ability to detect certain types, basic types of logic errors without actually executing the code, which is kind of cool. We're also thinking of adding Yang lent at some point here as well to do some syntax checks and validation against the Yang model. And actually, just recently, I was also thinking of adding coverage. So there's a coverage tool for Python, and there's a way to hook it into the NSO Python VM. So particularly when we're executing these tests, so we can see how well our tests are hitting the various pieces of the package code. And if we're missing any, more importantly, of course, if we're missing anything where we should add additional tests to, pick up try to cover, and try to effectively hit as much coverage as possible. And one of the key tools we make use of is Cisco's modeling lab. So that's a simulation environment that can be driven by a northbound API. And it's actually it's a fairly robust environment. And it lets us create a set of test tools on the fly of various types, test instances, device instances of various types. And we can place test config on those devices and import them and import that config into NSO when the care package as Mitch described, that's where the care package can get access to it and run against it. And our current lab, test lab in CML consists of each of the device types that care can handle. So it's basically iOS XE for layer 2 and layer 3. It's NXOS, it's iOS XR. We're looking to also add some scale testing if we can. It's on my monstrous plate of backlog stuff to look at, where we want to spin up, let's say, 50 or 100 devices and make sure there's not some, sort of scale issue, unforeseen scale issue when it's running against, quite a number of things. And we also use a custom NSO container image, which is just basically a version of NSO that's pre-installed on top of an Ubuntu 2004 base. And that install includes some of the utilities I mentioned, like Pilot and XML-LAN. And having that pre-built container actually saves some time in the pipeline. Of course, we could have included a stage or stages in the pipeline to dynamically build that container on the fly, but that's not what we're focused on here. So it was just, easier to have it available ahead of time. So we just periodically rebuild that container with if there's a new version of NSO that we want to incorporate into the test pipeline. And we also use a tools container that's available within Cisco, and it's just a nice bundling of some test tools. And that container is referred to as CXTA, and I believe that stands for CX testing and automation. And it includes kind of tools we're interested in, Ansible, the robot framework. There's some other stuff there. Robot, if you are unfamiliar with it, it's a open public domain package that can be used to execute various tests against things. And we make heavy use of that, as you'll see in a future kind of slide that's coming up here. So what's the pipeline look like? So this is a classic view of Jenkins taken from the Jenkins web server we're using, showing some runs, I believe from the end of last month, August 31st. So the columns here show the individual stages, and the rows are the different runs. So you can see there were 3 runs that this is showing. Not counting the initialization and post-action stages, there are 5 main stages in the middle. And as you can see, at this point, if you look at it, it was the average time for the entire pipeline to execute was taking about 24 minutes, and that's hundreds of tests against those templates. So the bulk of the time is being spent in the functional test stage, which is the 5th column over. And that's where the individual STIGs are being run against the configs in the NSO instance that's synced with our test devices in CML. And we'll go into a bit more detail on what each stage is doing in the next slide. And just to point out, the stages and the steps that make up each stage are defined in a Jenkins file that's part of the care repo. And any changes we make to that file, let's say, I was talking about a scale testing stage. So we're going to say we're going to add a new stage, or we want to add additional steps to one of the existing stages, or there's some parameter change like we wanted to execute against a different CML server, for example. That's all picked up by Jenkins before the pipeline starts to run. So it's just kind of dynamic. If we push a change to the Jenkins file, then the very next run of the pipeline will incorporate that change. Okay, so let's walk through some detail as to what's happening in each of these pipeline stages. And I thought it'd be interesting to go through this level of detail so you can better appreciate the steps involved. And I realize this slide's a little busy, but I've added some animation that we'll walk through. We'll hopefully make it a little easier to follow. Just watch for there'll be a red arrow that shows up here in a second. And the steps are color-coded to match the Jenkins stages that are shown at the bottom in yellow, green, pink, purple, whatever. So you can tell which steps belong to which stage. And to point out, there are 3 stages, 1, 2, and 3 steps, 1, 2, and 3, which I put those in red because they're happening outside the pipeline, really. And also the animation is going to skip over a couple of steps here just for the sake of time. So first, what happens? Someone, like Mitch, me, whoever, pushes a change to the repo. That could be a code change. It could be a change in one or more of the templates. It could be a change to the Jenkins file, anything. So that will trigger a webhook, which is just an HTTP post to a target URL, and that target URL is on the Jenkins server. And the post payload that's sent with that webhook, that includes the repo involved and who triggered it, what triggered it, and some other information. So that shows up at the Jenkins server, and it's going to be handled by the generic webhook plugin that Jenkins has. And the plugin will match the info in the payload against the defined pipelines on that Jenkins server, and ends up triggering the one for care because it'll, again, match the repo against the entry for that particular pipeline. Okay, so now we're entering the initialization stage of the pipeline. You can see the yellow stage at the bottom. I highlighted it in red. So this stage uses a Jenkins Git plugin to clone the current repo contents into the Jenkins workspace. And that workspace is really just, it's a directory that's mapped into the Jenkins instance on this particular, Jenkins server. So the next stage is a project update. So this is the first thing this stage does is basically launch an instance of our custom NSO container, and it maps that Jenkins workspace into it, so it's available as a local directory effectively. Then the stage executes an NCS project update, and that ends up, among other things, it ends up fetching any required NEDs as defined by the project metadata. And the way we have that metadata currently set up is we tell it to pull the NEDs from an via HTTP from an internal server. We just keep the NEDs we need out there. All right, then that executes a make all, and that just effectively triggers, again, among some other things, it triggers a recompile of the CARES Yang model into an FXS file. Okay, so now we're up to the syntax check stage. So that's going to use another make target to trigger the code check, code quality check, linting, quote unquote. So, and I should point out, any error here or in any of the stages will cause the pipeline to fail, and any subsequent stages will be skipped. So if we had a syntax error or something that the make check picked up, we certainly had that happen, then the rest of the pipeline stages aren't executed, and we'll see there was something went wrong. All right, so far so good. Now we're entering the setup for the functional test. So this is kind of the meat of it. So this stage first launches an instance of the CXTA container. And here we're really just using that container to provide access to Ansible. And Ansible is going to be used to talk to the CML server's northbound API. And the playbooks used for this are held in a testing related section of the care repo. And a series of those playbooks are used to, of course, to communicate with the API. As part of that, it's going to upload our predefined lab file into CML. There was a question earlier that's where in the Q&A, that's where the test topology actually comes from. It's defined in that test file. And so that tells CML what test instances are needed, what types they are, and how they're connected to each other. Basically, it's going to launch those instances in a controlled sequence. The playbook takes care of that. Once they're launched, another playbook will then wait for those instances to become ready, and that can take several minutes. I think I've seen it take 4 or 5 minutes. It just depends on the devices. But it'll wait till they become ready. It'll also wait until they've DHCP'd for a management address. And once they've got their management addresses, the playbook will then take that information and combine it with information in the Ansible inventory and a Jinja 2 template we've got to generate a set of device info, which can be loaded into NSO in the next stage to tell it how to communicate with those test instances. It also generates a robot testbed file too that tells robot how to communicate with those test devices as well. So it's kind of, whatever dynamic address they happen to get, we'll latch onto that and hook everything together. And note at the end of this particular stage, that instance of the CXTA container exits because we just needed it to get access to Ansible at this point. Okay, so now we're moving to the actual functional test. So this stage first launches an NSO container instance, and a make start is executed to start the actual reference NetSim instances that CARE uses internally. It launches the main NSO NCS process. That picks up that test info that we generated earlier, so now it knows how to communicate with the devices. It also picks up, of course, the NEDs and the care package itself. And we end up at this point running some show commands to log the package versions and the device info being used, so we can see it in the Jenkins log just for information purposes. And then we launch another CXTA container. And now this is interesting because now that we have NSO and CXTA running in parallel with each other, and they're actually communicating across a user-defined private Docker network, so they can see and talk to each other on the Jenkins server. I'm sure I'm hitting the right point. Then the next thing it's going to do is run a script, run robot script that picks up all our test scripts with all the template tests in it. That's run by robot. And the first thing each one of those test scripts does is, in every case in ours, is pushing a test config at one or more of those test devices. And that config is effectively just a setup for that series of template tests. And we purposely bypassed NSO at this point to put the config on the devices because we wanted to better simulate or more closely simulate what would be happening in a real network where NSO has been told to sync to connect to some set of devices and sync config in. So we chose not to go through NSO to do this portion, just go straight to the devices. And then that robot basically is communicating with NSO via the NCS process, via its CLI and RESTconf interface. And at this point, it's going to tell it to do the sync from, which I will skip over. And then it will use the RESTconf interface to basically walk through each of the template tests. And it's done via an action within the care package. So it's a RESTconf call to action. We'll see more detail about that in a second. And as robot's executing, it's generating a pretty nice test output file, which we'll see. And once all of this is done, all those tests are finished executing, then we'll tear down the NSO container, the CXDA container, and actually another stage, the cleanup stage, will launch another CXDA container that, again, uses Ansible to tell CML to just tear everything, tear the whole test environment down and exit. And at the very end of this, we can choose, depending on how we trigger the pipeline, we can get an email back saying, yeah, this pipeline run worked or it failed for whatever reason. And that test output, and along with the device configs and some other log files, are bundled together and made available as an artifact by Jenkins that we can go to the Jenkins web interface and just click and download that, and we'll again see what that report looks like here in a second. So what do one of these robot test scripts look like? I picked this one as an example, just to give you an idea of what it's doing as a setup. So robot runs, it's a Python, robot's a Python-based package, I think I might have mentioned, and it uses a series of keywords, and the keywords can typically consist of one or more steps. So if you look under that test cases portion of this, you can see there's a setup for the template test. That's where we record the target device configuration for a particular device. We connect to the device. Then another next keyword, like third one up from the bottom, is load that initial configuration I mentioned. And then it's going to start stepping through the template tests. And you can see there's a couple of them at the bottom here that have a tag on them just so we can identify the test. And then it can have one or more template test calls for that template with a particular action like Mitch showed, check, print, fix, a test number, and then a target device. And that thing at the end is the empty is shown here because neither of these templates require it. But that's where we could drop in a listing of variable and values if a particular template requires it. And of course, we could run a template with one set of values, change the values, and run the template again. So pretty flexible testing setup. And what does that robot test keyword look like? So this is one we wrote. So that just to show you the steps it's executing for each of the template tests. It's effectively constructing an XML payload to send to NSO on the RESTconf API that it triggers the action within the care package. It processes the result. Of course, we're checking for HTTP errors or any kind of other error coming back from the NSO API. And the final step at the bottom is probably the most interesting one. That's where it's comparing what came back from NSO for this particular call against what we expected to come back. And those expected outputs are held in the repo, the care repo, under the test section. And it's basically just a series of files that are organized by the test type, print, check, fix, whatever, the template name, and a test number for that particular template, just so we can keep them straight and organized. So now let's take a look at one of these, what one of these reports looks like, because it's actually kind of cool. Switch to this display. So this is a care report. Let me zoom in. This is an HTTP-based report that Robot generates at the end of the, basically while the pipeline's running, and then the summary's generated at the end. And you can see it's pretty, just the fact it's got a red background tells me that one or more of the tests failed. I picked this particular report, but it was run over a month ago. It was run toward the beginning of August, because it does show some failures, just as an example. And you can see at this point in time, of 327 total template tests, 8 of those were failing. And down here, there you can see the statistics by suite. And what Robot's calling the report is what it's calling a suite at this point is one of our collections of tests within a particular file. So you can see there's 7 suites, so 7 sets of tests across 7 files. And there's a breakdown, of course, within each file of the total number of tests, how many passed and how many failed. So let's pick this particular one here, this negative template test on NDM templates against an XE device, just because it has some failures in it. Again, this is an HTML-based report, so I can just click into it, and we'll see the detail about the steps that were executed for this group of tests. So here's that load initial config test that I mentioned in the, or showed you in the Robot test script earlier. If I click into that, expand it again, I can see the tests, the actual steps that keyword executed. And again, probably the most interesting one is this configure test, where it's actually pushing some config at a device. Let me zoom in again. Here I can see the actual config that was pushed as the setup for this series of tests. And here, this actually shows me Robot's actual interaction with the console of the test device via Robot's console driver. And here I can see it executing the config term and issuing all the config commands as the setup for this. And if there's any syntax errors or anything, again, we've certainly made our share of syntax errors setting this stuff up. If there's any problem that Robot encounters while it's pushing this config at the device, of course, we'll see that in this log, which makes troubleshooting the test setup kind of nice. Let me back out of this test. And let me show you a successful test first. So this is, the commits use this template as an example as well. So this is ND number 10. And click into this. So here's the template test keyword as it's executing. And here's a log for each of the steps that comprise that keyword. And probably, again, one of the more interesting ones is this line right here. This is when Robot issued the RESTconf call via a post to NSO to CARE's action, basically action to trigger a test. And you can see the payload that was constructed and sent to NSO. I can see the response coming back from NSO with the HTTP-based, of course, status code. So that's, again, nice to see exactly what NSO got and what it sent back to us. And let me, of course, this is all error processing checking. Let me skip down to the bottom. So here's the comparison check of what came back from NSO against, again, what we expected to come back. And in this case, they compared exactly. So this test was declared a success. So that's, kind of interesting, but not that interesting. Let's pick one that failed. And here's one. So 590 stands out because the test word is in red. I know that there was a problem with this one. Let me expand it. Let's just go straight down to the comparison. So this is nice, a nice level of detail. Here's the comparison. This is effectively a Unix diff output. So what Robot's showing me in this case is what came from NSO, which is string 1 here in red, and against what we expected to come back, which is shown in green on the right. And like a Unix diff output, this shows you what was present on one side that wasn't present on the other side, and vice versa. So I can see that those don't compare at all, again, due to a net issue at the time, if I remember right. So of course, these failed the comparison, so this test was declared a failure. scroll down to one that might have a different output. So here's another failure. Oh, and this one's interesting too, because you can see here the example of where we're passing in a variable and a value, because this particular template requires a log host variable to be passed in. If I look at the API call to NSO, I can see here in the payload where that variable was passed into as part of the API call. Let's scroll down to the comparison. So this one's a little different. We got part of what we expected to come back, the logging host, no logging host, but we also expected a line logging trap informational, which did not come back. And you can see that's highlighted in green, so it makes it stand out. So again, due to a net issue, I believe. So again, these contents differ, so the test was declared a failure. So nice level of, like I said, troubleshooting detail that this is providing. And let me show you an example of another one of the files that Robot gives us. So this is a device log example. Zoom in on this. It's got a little more detail than what I showed you in the HTML report. So here I can see it actually SSHing to the device, logging in. This happened to be a cloud services router instance. I can see Robot, its console driver, executing some setup commands to make the output coming back from the device a little easier to process. And if I scroll down here, of course, here's where it dropped into the config term, and there's the commands being issued, kind of the same output we saw in the HTML-based report. Again, if there was a warning or an error or a syntax problem or something that came back from the device, indicated by the device, we'll see the output here, and helps us troubleshoot if we made a mistake or something in the config setup for this series of tests. Let me drop back to the presentation. So that's an example of the report. So kind of summary, we think automated testing like this is a great addition to have in any NSO package or project you're working on. We feel it's added an increased level of confidence in the care package code, template code, and Python code. And we're actually at this point, based on what we've experienced doing this, we're actually motivated to add even more tests to try to recover even more bases. Again, trying to root out any problems before a user gets a hold of it. And as you've hopefully seen, this type of setup, along with the tools we've used, we think makes this type of automated testing of NSO packages and the package functionality fairly straightforward to implement. And as a final comment, of course, obviously the quality of the testing you're going to do is only as good as the test cases you can come up with, and the quality of those test cases and the variety of those test cases.